Let me start with something that will genuinely disturb you if you sit with it long enough. Right now, you are sitting somewhere on the surface of a planet. That planet orbits a star. That star sits inside a galaxy, a vast spinning collection of roughly 200 to 400 billion other stars. You are, by any reasonable definition, surrounded. There is matter above you and below you. There are planets in your solar system, stars in your galaxy, gas clouds blooming across your cosmic neighborhood like enormous bruises in space. You are embedded deeply in a universe that seems stuffed full of things. Every direction you look, there is something. There is something to look at, something to measure, something to wonder about. And yet, the overwhelming majority of the universe, the vast, staggering, truly incomprehensible majority of it, is not this. It is not planets. It is not stars. It is not gas clouds or black holes or spinning neutron stars the size of a city. It is not any of that. The overwhelming majority of the universe is the space between galaxies, the gap, the void, the nothing. And here is the thing I want you to understand before we go any further. The thing that will underpin everything else we talk about today. When scientists use the word nothing to describe intergalactic space, they are not being poetic. They are not rounding down. They are not speaking loosely for the sake of an audience. They mean it in a way that is almost impossible to fully communicate in human language, because human language was built by creatures who have never, not once in the history of their entire species, experienced a vacuum anywhere close to what exists between galaxies. The gap between galaxies is not empty the way your living room is empty when no one is in it. It is not empty the way a swimming pool is empty when you drain it. It is not even empty in the way outer space feels empty when you imagine astronauts floating between the Earth and the Moon. It is empty in a way that is qualitatively fundamentally different from anything your brain is equipped to model. Because your brain, remarkable as it is, was built for a world where emptiness is always temporary. Where there is always something on the other side of the empty space. Where the vacuum is never truly absolute, but the gap is truly absolute, and it gets worse. Because it is not just that the gap is incomprehensibly empty, it is that the gap is incomprehensibly big, and it is not just that it is big, it is that it is growing, and it is not just that it is growing, it is that the rate at which it is growing is accelerating, and it is not just accelerating, it is accelerating in a way that suggests, if you run the numbers forward honestly and without flinching, that the future of the universe is not more stuff and more complexity and more interesting things to look at. It is infinitely more nothing. It is the void winning slowly and inevitably and without any mechanism that could possibly stop it. So settle in, because by the end of this video, you are going to understand the gap between galaxies in a way that most people, including, honestly, most people who consider themselves science enthusiasts, have never fully confronted. You're going to understand what is actually in that gap. What is actually happening there on scales that dwarf anything our civilization has ever attempted to grasp. What it means for the structure of the observable universe, and why the cosmos you think you inhabit is, in the deepest possible sense, almost entirely absent of anything at all. Let us start with the most important thing. Let us start with scale. Chapter 1. The Scale Problem. The single biggest obstacle to understanding intergalactic space is not physics. It is not mathematics. It is not even the alien weirdness of quantum mechanics, or the mind-bending geometry of general relativity, both of which are in their own ways deeply strange. The single biggest obstacle to understanding the gap between galaxies is the fact that human brains are, from a cosmic standpoint, laughably inadequate at processing large numbers. We evolved on the African savanna. We evolved to understand distances measured in meters, maybe kilometers on a good day. We evolved to care about things we can see and touch and smell and at least imagine. And while we have gotten remarkably good, through centuries of science and mathematics, at representing cosmic distances, at writing them down on paper and manipulating the symbols and feeding them into equations, we have not gotten much better at actually feeling them, at viscerally, intuitively understanding what they mean in a lived human sense. So let me try something different. Let me try to build up to intergalactic distances the hard way, by walking you through the chain of scales, one step at a time, letting each scale do its full work on your imagination before we move to the next one, until the full scope of the gap becomes something you cannot look away from. start with you. You are, let us say, roughly 1.7 meters tall. That is your reference point. That is the thing your brain can hold in its entirety, the scale it was built to understand. Now, zoom out. The Earth is about 12,742 kilometers in diameter. That is roughly 7.5 million of you, standing head to toe in a straight line. Already your brain is starting to strain. You can hold the number 7.5 million in your working memory. You can write it down. You can do arithmetic with it. But you cannot feel it. You cannot intuitively grasp what it means to stack 7.5 million of yourself end to end, because your intuitive number sense stops working somewhere around the scale of a sports stadium and replaces everything larger with a vague, undifferentiated sense of very large. Brain researchers call this magnitude estimation collapse. It is the reason lottery jackpots stop feeling meaningfully different above a certain point. The universe does not care about this limitation. The universe keeps going anyway. The Earth is about 150 million kilometers from the Sun. Put another way, light, traveling at 300,000 kilometers per second, the fastest possible speed in the universe, takes about 8 minutes and 20 seconds to cover that distance. 8 minutes. From the surface of the Sun to the surface of the Earth, light travels for roughly the same amount of time it might take you to make a cup of coffee. That distance is called 1 astronomical unit, or 1 AU, and it is the baseline unit of measurement for our solar system. Now move out to the edge of what we might loosely call the solar neighbourhood. The Oort cloud, the vast and nearly invisible shell of icy objects that marks the outermost extent of the Sun's gravitational influence, stretches out to somewhere between 1,000 and 100,000 astronomical units from the Sun. The inner edge of the Oort cloud is perhaps half a light year away. The outer edge may be as much as 3 light years away. That is 3 years of travel at the speed of a light just to reach the outermost fringe of our own solar system. And our fastest spacecraft, Voyager 1, which launched in 1977, which has been flying outward for over 40 years, which is the most distant human-made object in history, reached the edge of the heliosphere, the boundary of the Sun's direct influence, only around 2012. It has not yet reached the Oort cloud. At its current speed of about 17 kilometers per second, Voyager 1 would take approximately 300 years to reach the inner Oort cloud, and roughly 30,000 years to pass through the outer edge of it. 30,000 years! Bronze Age civilizations had not yet risen the last time the Earth was at the point in human history it would need to be at for Voyager 1 to finish that journey. And Proxima Centauri, the nearest star to our Sun, is 4.24 light-years away. That is about 40.2 trillion kilometers. In a scaled model where the Sun is at the center and the Earth is 1 centimeter away, Proxima Centauri would be about 2.7 kilometers away. 2.5 miles. That is the nearest star. That is our immediate neighbor, and it would take Voyager 1 roughly 73,000 years to reach it at its current speed. Now here is the thing about Proxima Centauri that matters for our purposes. It is barely anywhere. It is not even a rounding error in terms of galactic distance. The Milky Way galaxy, our home galaxy, is somewhere between 100,000 and 200,000 light-years across. It contains somewhere between 200 billion and 400 billion stars, and Proxima Centauri, at 4.24 light-years, is about 0.004% of the way across it, a tiny fraction of a tiny fraction. The Milky Way is a flat spiral disk with a central bulge and a surrounding halo. Its disk is roughly 1,000 light-years thick in most regions. Our Sun sits about 26,000 light-years from the galactic center. If you were to compress the Milky Way to the size of a dinner plate, 25 centimeters in diameter, our Sun would be a speck of dust about 9 centimeters from the center, and a human being at that scale would be so small as to be invisible by any instrument we could conceivably build. And the nearest large galaxy to the Milky Way, Andromeda, M31, the nearest galaxy comparable to ours in size and complexity, is 2.537 million light-years away. Let that settle. 2.5 million light-years. If you were travelling at the speed of light, you would leave the Milky Way, travel for 2.537 million years, and then arrive at Andromeda. During that journey, during that entire incomprehensible stretch of travel, you would pass through mostly nothing. The local group, the small collection of galaxies that includes the Milky Way, Andromeda, and roughly 50 to 80 dwarf galaxies, is spread across a region about 10 million light-years in diameter. That is 10 million light-years, mostly empty space, containing perhaps 80 galaxies. Now compare the gap to the objects themselves. The Milky Way is about 100,000 light-years across. Andromeda is about 220,000 light-years across. The gap between them is 2.537 million light-years, roughly 25 times the diameter of the Milky Way, or about 12 times the diameter of Andromeda. In our dinner plate model, if the Milky Way were a dinner plate 25 centimeters across, Andromeda would be about 5 meters away. Across a medium-sized room, 2 dinner plates sitting in the same house, and the local group sits within the Laniakea supercluster, a structure so vast and so loosely connected that it was only properly mapped and named in 2014 by a team led by cosmographer R. Brent Tully. Laniakea stretches across approximately 520 million light-years and contains an estimated 100,000 large galaxies and a total mass of about 100 million billion solar masses. It is one of the largest structures in the observable universe, and beyond Laniakea, and beyond the Perseus-Pisces supercluster, and beyond the Shapley concentration, and beyond every named structure you might have heard of, is the observable universe itself. A sphere roughly 93 billion light-years in diameter, containing somewhere between 200 billion and 2 trillion galaxies, bounded not by a wall or an edge, but by the limit of how far light has had time to travel since the Big Bang. 2 trillion galaxies in a sphere 93 billion light-years across. When you hear that number, it sounds dense, it sounds full, it sounds like a universe jammed with structure and complexity and interesting things to look at in every direction. But run the arithmetic. A sphere 93 billion light-years in diameter has a volume of approximately 4 times 10 to the 80 cubic meters. Distribute 2 trillion galaxies across that volume, and each galaxy gets, on average, about 40 billion cubic light-years to itself. A cube of space 3.4 million light-years on each side, all for one galaxy. And that is the average. The reality is more extreme. Because galaxies are not distributed uniformly, they cluster into filaments and sheets and walls, leaving behind enormous regions of space with almost no galaxies at all. The cosmic voids. Regions hundreds of millions of light-years across containing almost nothing. By volume, and this is the number that should actually change how you think about the universe, by volume, the cosmic voids make up somewhere between 80 and 95% of the observable universe. The filaments and walls and clusters of galaxies, for all their grandeur and complexity, occupy the remaining 5 to 20%. The universe, looked at honestly, is not a dense field of galaxies. It is an almost empty ocean of nothing, with a thin web of matter stretched across it like a cobweb in a cathedral. That is the universe you live in. Chapter 2. What is actually in the gap scale is one thing. Emptiness is another. So let us talk about what is actually in the gap, because it is not literally nothing, and the details of what is there are as strange and fascinating as the emptiness itself. Let us start with ordinary matter, the kind of matter you are made of. Protons, neutrons, electrons, the stuff physics textbooks call baryonic matter. Within a galaxy, the density of matter is relatively high, at least by cosmic standards. The interstellar medium, the gas and dust between stars inside a galaxy like the Milky Way, has an average density of roughly 1 atom per cubic centimetre. In dense molecular clouds, where new stars are actively forming, it can reach a million atoms per cubic centimetre. In hot diffuse regions between the spiral arms, it drops to perhaps 1/100th of an atom per cubic centimetre. This is already an extraordinarily good vacuum by Earth standards, but it is rich, lush, almost crowded compared to what lies beyond the galaxy's edge. In the intergalactic medium, the IgM, the gas that fills the spaces between galaxies, the density drops by a factor of roughly 1 million. The intergalactic medium has a density of somewhere between 1 and 10 atoms per cubic metre. Not per cubic centimetre, per cubic metre, a cube of space 1 metre on each side, a cube you could step into and stand in the middle of, and that entire cube in the intergalactic medium contains maybe a handful of particles. Here is a comparison that I think actually lands harder than the astronomical numbers. The best vacuum we can achieve in a laboratory on Earth, the kind of vacuum maintained inside particle accelerators, the kind that requires enormously sophisticated engineering and constant active pumping, the kind that represents the current frontier of human vacuum technology, has a particle density of roughly 10 million molecules per cubic centimetre. That is 10 to the 7th power molecules per cubic centimetre, or about 10 to the 13th power molecules per cubic metre. The intergalactic medium has a density of about 10 atoms per cubic metre, so the intergalactic medium is roughly 10 to the power of 12 times less dense than the best vacuum we can create on Earth. 1 trillion times more empty. 1 trillion. And the best laboratory vacuum we can create is already so empty that it makes human intuition feel completely broken. It is already a vacuum so extreme that it is, for almost any practical purpose, indistinguishable from nothing at all. And the intergalactic medium is 1 trillion times more empty than that, but it is not literally nothing. And the things that are there are worth understanding. The intergalactic medium is mostly hydrogen, roughly 75% by mass, with about 24% helium and trace amounts of everything else. This is the primordial composition, the chemical fingerprint of the Big Bang, barely altered by the billions of years of stellar nucleosynthesis that has taken place inside galaxies. It is ancient gas, mostly untouched since the universe's first few 100,000 years, and it is unimaginably hot. The intergalactic medium, at least the fraction of it that exists in the regions between and around galaxy clusters, called the warm-hot intergalactic medium, or WEM, has a temperature of roughly 100,000 to 10 million Kelvin. To give you a sense of that, the surface of the Sun is about 5,800 Kelvin, the core of the Sun is about 15 million Kelvin. The WEM, with its 10 million Kelvin temperature, is approaching solar core temperatures. It is, in a technical sense, extraordinarily hot. And here is the paradox of that, the thing that sounds almost philosophical when you first hear it. A gas that is almost completely absent, that has effectively no density, can still have a temperature, because temperature is not about how much matter is present. It is about the average kinetic energy of the particles that are present, however few there are. Those handful of atoms per cubic meter are moving extremely fast, bouncing around with enormous kinetic energy, and that motion defines the temperature of the medium, even though there are so few of them that the concept of temperature feels almost metaphorical. This hot, thin gas, the WEM, is actually one of the more important and mysterious things in modern astrophysics, and here is why. For decades, cosmologists noticed that when they added up all the ordinary matter they could observe in the universe, all the stars, all the gas in galaxies, all the gas they could detect around galaxies, they only accounted for about half of the baryonic matter the Big Bang nucleosynthesis models predicted should exist. The Big Bang, as best as we can calculate it, should have produced a certain ratio of protons, neutrons, and electrons, a certain total amount of ordinary matter, and for a long time we could only find about half of it. The other half was simply absent from the cosmic ledger. This was called the missing baryon problem, and it was genuinely embarrassing as cosmological problems go. We had a model, our best model, that predicted a certain amount of stuff and roughly half the stuff was missing. The answer, pieced together, over the past 2 decades from increasingly sensitive X-ray and ultraviolet observations, is that the missing baryons are in the WEM. Half of all the ordinary matter in the universe, half of all the protons and neutrons and electrons, is not in galaxies. It is not in stars or planets or gas clouds you could point at with a telescope. It is stretched thin across the enormous filaments and sheets of the cosmic web, heated to millions of degrees by shock waves from galaxy formation, and distributed so diffusely across such enormous distances that it was essentially invisible to us until we knew what to look for. The stuff you're made of is a cosmic minority, and most of that minority is invisible gas floating between the galaxies. There is also the matter of the Lyman alpha forest, which is one of the most beautiful and scientifically powerful tools we have for probing the intergalactic medium. When light from a very distant quasar travels toward us across hundreds of millions or billions of light years, it passes through countless tendrils and sheets of the intergalactic medium. As it passes through each cloud of hydrogen gas, the gas absorbs a very specific wavelength of light, the Lyman alpha wavelength, 121.6 nanometers in the ultraviolet, but because each cloud is at a different distance and therefore receding from us at a different velocity, each absorption happens at a slightly different wavelength due to the Doppler effect. The result, when you look at the spectrum of a distant quasar, is a forest of absorption lines, the Lyman alpha forest, each line corresponding to a different filament or sheet of intergalactic gas along the line of sight. The Lyman alpha forest is, in effect, a map of the distribution of matter along a single line of sight through the universe, reaching back billions of years. By analysing thousands of quasar spectra, cosmologists can reconstruct the three-dimensional density structure of the intergalactic medium across cosmic time. It is one of the primary ways we've tested our models of large-scale structure formation, and the agreement between theory and observation is, genuinely, one of the great intellectual achievements of modern science. But what the Lyman alpha forest also tells us is that the intergalactic medium is not featureless. It has structure. It is denser in the filaments, less dense in the sheets, and almost entirely absent in the void interiors. Even the nothing has texture. Even the gap has a shape. Then there are the magnetic fields. Intergalactic magnetic fields are almost impossibly weak, potentially as weak as a femtogauss, which is 10 to the power of minus 15 Gauss, compared to the Earth's surface magnetic field of about half a Gauss. They are roughly 10 to the power of 15 times weaker than the Earth's field. They are so weak that detecting them requires indirect methods, looking at the polarization of radio waves from distant sources, studying how they rotate the plane of polarization of light that passes through them. And yet they exist, extended across enormous scales, threading through the voids and filaments of the cosmic web. Their origin is one of the genuinely open questions in cosmology. Did they form before the first galaxies, seeded by processes in the very early universe? Were they blown out of the first galaxies by stellar winds and supernova explosions, slowly filling the intergalactic medium over billions of years? We do not know. Then there is dark matter, present even in the voids, though less dense there than in the filaments, threading invisibly through all of it. And then there is dark energy, which doesn't cluster at all, which is distributed uniformly throughout every cubic meter of space, which in the voids, where matter's counteracting gravity is weakest, operates entirely unchallenged. The gap is not empty, it is just almost empty in a way that makes everything on Earth feel crowded. Chapter 3: The Cosmic Web and Why the Gap Exists. Before we go deeper into the nature of the void, we should step back and ask a question that turns out to have a remarkable answer. Why does the gap exist at all? Why are galaxies not distributed smoothly and uniformly through space? Why is the universe arranged in this extraordinary web of filaments and sheets, leaving enormous empty voids behind? The answer goes all the way back to the beginning of everything, to the first tiny fractions of a second after the Big Bang, and it is a story about how almost nothing can become almost everything. The early universe, in the first seconds and minutes after the Big Bang, was not perfectly uniform. If it had been, if the distribution of matter and energy had been absolutely homogeneous in all directions, then the universe today would look completely different from what we observe. There would be no galaxies, no stars, no planets, no chemical complexity of any kind. Just a smooth, featureless fog of gas, slowly cooling and expanding forever. A universe in perfect thermodynamic equilibrium, beautiful in a mathematical sense and completely, utterly dead in any meaningful sense. But the early universe was not perfectly uniform. It was almost perfectly uniform. The fluctuations in density, the tiny variations from place to place in how much matter and energy was present, were of order 1 part in 100,000. In a room at average temperature, that is like having one spot on the wall that is 0.001 degrees warmer than average, an almost imperceptible ripple on the surface of otherwise perfect homogeneity. These fluctuations were quantum mechanical in origin. In the inflationary epoch, the first tiny fractions of a second after the Big Bang, the universe underwent a period of extraordinary exponential expansion, space itself doubling and doubling and doubling again at an incomprehensible rate. During this process, quantum fluctuations in the energy of the inflaton field, tiny, random variations of the sort that are inevitable given the laws of quantum mechanics, were stretched by the expansion from subatomic scales to cosmological scales. What began as a quantum whisper became a cosmic echo, imprinted across the entire fabric of space. And then gravity went to work. In the slightly denser regions, gravity pulled matter together. More matter meant stronger gravity. Stronger gravity pulled in more matter. More matter created even stronger gravity. Over hundreds of millions of years, This runaway process of gravitational collapse built the first stars and the first galaxies. The dark matter, which does not interact with the radiation that was filling the early universe, was free to start collapsing even before ordinary matter could, forming the gravitational scaffolding, the dark matter halos, into which ordinary matter then fell, cooled, and condensed into stars and galaxies. In the slightly underdense regions, the process ran in reverse. It is important to understand this carefully because it is counterintuitive. The underdense regions were not being pushed outward by some anti-gravitational force. Gravity in those regions was simply being outcompeted. The slightly overdense regions surrounding each void were pulling more strongly on the matter at the void's edges than the void's interior was pulling on it. Matter drained away from the void's center toward the surrounding overdense regions, leaving the void emptier over time. The void did not empty because something pushed the matter out. It emptied because the matter at its edges was pulled away by the surrounding cosmic structure. This is a process that has been running for 13.8 billion years, and it has continued running because of a crucial feedback mechanism. As matter drains away from a void, the void becomes less dense, which means it contributes even less gravitational pull, which means matter drains away from it even faster. The voids have been emptying themselves progressively over the entire age of the universe. The result is the large-scale structure we see when we map the distribution of galaxies across the observable universe. The extraordinary maps produced by surveys like the Sloan Digital Sky Survey or the more recent DSI survey show a universe that looks uncannily like something organic, like a neural network, like a slime mold, like the blood vessel structure of some immense and invisible animal. Galaxy filaments stretching across hundreds of millions of light years, connected at nodes where rich galaxy clusters sit, separated by enormous spherical voids that look almost deliberately carved out. This structure is called the cosmic web, and it is, in the most literal sense, the large-scale shape of the universe. The largest well-studied void, the Butter's Void, discovered in 1981, is approximately 330 million light-years across. It was so unexpectedly empty when it was first mapped that the astronomer who discovered it reportedly said it was large enough to swallow multiple cosmic structures and leave no trace. If the Milky Way had been located at the center of the Butter's Void, humanity would not have been able to discover any other galaxies until the development of radio telescopes sensitive enough to detect the faint glow of the intergalactic medium. The nearest galaxies would have been so far away that they would have been invisible to optical astronomy until the mid-20th century at the earliest. We would have lived for the entire history of our civilization in a universe that appeared, as far as we could tell, to consist of one galaxy. Just us, alone. That is what the gap looks like at its most extreme, and the Butter's Void is not even close to the largest void. The KBC Void, the region of space identified in 2013 by Keenan, Barger and Cowie, is roughly 2 billion light-years in diameter, making it one of the largest known underdense regions in the observable universe. Some researchers believe the Milky Way actually sits within this enormous underdensity, which could explain some of the tension between different measurements of the Hubble constant that has been troubling cosmologists for years. The possibility that we live inside a void, that our galaxy is itself located in one of the universe's great empty regions, is not settled science, but it is a serious proposal taken seriously by serious people. The implications of void structure for galaxy formation are profound and somewhat counterintuitive. Cosmological simulations show that voids are not just passively empty, they actively shape the galaxies on their boundaries. The outflowing matter from voids, streaming toward the surrounding filaments, carries with it momentum and angular momentum that influences the rotation and orientation of the galaxies that form in those filaments. The void environment leaves a measurable imprint on the properties of galaxies, their shapes, their star formation rates, their chemical compositions, that can be statistically detected and used as a probe of the expansion history of the universe. In other words, the voids are not just empty space, they are dynamic structures that influence everything around them. They have a kind of gravitational shadow cast outward across their boundaries. They are actively participating in the ongoing evolution of cosmic structure, billions of years after the initial density fluctuations that created them. There is even a field of research, void cosmology, dedicated to using voids as precision tools for measuring the universe's expansion rate, testing theories of dark energy, and probing the laws of gravity on the larger scales. Because the void interior is so clean, so free of complicating matter, it is in some ways an ideal laboratory for cosmological physics. Anything you measure in a void is measuring the universe at its most fundamental, most undisturbed, most purely geometric. The emptiness is not wasted. The void is doing work. Chapter 4. The Expansion and the Growing Gap. In 1929, Edwin Hubble announced one of the most consequential scientific findings in human history. By systematically measuring the redshift of light from distant galaxies, the stretching of their light toward longer, redder wavelengths that occurs when an object is moving away from you, Hubble found that virtually all galaxies are receding from us. Not just a few, and not just the ones in certain directions, but essentially all of them, in all directions. And he found something more. The farther away a galaxy is, the faster it is receding. The universe is expanding. It is important to understand precisely what this means, because there is a very common and very wrong way to picture it. The galaxies are not moving through space like billiard balls or rockets. They are not projectiles launched from some central explosion, spreading outward through a pre-existing empty space. The space between the galaxies is itself expanding, growing, stretching, the way the surface of a balloon stretches when you inflate it. If you put dots on a balloon and blow it up, every dot moves away from every other dot. The dots themselves are not moving relative to the balloon's surface, it is the surface that is growing, and from any dot's perspective, every other dot is moving away, with more distant dots appearing to move faster. There is no center, there is no preferred location. Every point in the universe is, in this sense, the center. The rate of this expansion is quantified by the Hubble constant, denoted h0, currently measured at roughly 67 to 73 km per second per megaparsec, depending on which measurement method you use. A megaparsec is approximately 3.26 million light-years. So what this means, in practice, is that a galaxy 3.26 million light-years away is receding from us at 67 to 73 km per second. A galaxy 32.6 million light-years away, 10 megaparsecs, is receding at roughly 700 km per second. A galaxy 326 million light-years away is receding at roughly 7,000 km per second. At a distance of about 14 billion light-years, galaxies are receding from us at the speed of light. And here is the fact that should make you stop and breathe for a moment. The observable universe, as we noted earlier, is 93 billion light-years in diameter. The edge of the observable universe is roughly 46 billion light-years away from us, which means galaxies at the edge of the observable universe are receding from us at roughly 3 times the speed of light. Not because anything is moving through space faster than light. Einstein's relativity says no object can move through space faster than light, and that law holds exactly. But the expansion of space itself is not limited by the speed of light. Space can expand at any rate. What moves through space is limited. Space itself is not. So galaxies at the edge of the observable universe are not moving through space at 3 times the speed of light. They are stationary in space, and the space between us and them is expanding at 3 times the speed of light, carrying them away from us faster than light can travel toward us. What Hubble could not have known in 1929, and what takes some time to fully absorb, is the implication of the expansion for causality itself, for the flow of information through the universe. If everything is expanding away from everything else, and if there is a speed limit to information, the speed of light, then there must be regions of the universe that are permanently beyond communication with each other. Not temporarily out of reach, permanently. A galaxy so far away that the space between us and it is expanding faster than light cannot send us a message that will ever reach us, no matter how long we wait. It could fire a laser in our direction every second for the rest of time, and every one of those photons would be carried backward, away from us, by the expansion. From that galaxy's perspective, we might as well not exist. This is not a technological limitation. It is not something that could be overcome with better telescopes or faster spacecraft. It is baked into the geometry of an expanding universe. It is a fundamental structural feature of the cosmos. The universe is divided on the larger scales into causally disconnected regions. bubbles of observable reality that cannot, in principle, communicate with each other or have any influence on each other whatsoever. We're in one such bubble. Our observable universe, the sphere bounded by our cosmic event horizon, is, in a profound sense, all that can ever exist for us. Not all that exists, period, but all that exists in any causally relevant way. Everything outside the event horizon might as well be in a different universe, because no influence, no signal, no photon, no gravitational wave, no information of any kind can ever pass from there to here. The gap between galaxies is not just distance, it is isolation. It is the severing of any possible connection between vast regions of an infinite cosmos, and dark energy is enlarging those severed regions every day, expanding the boundaries of our irreversible cosmic solitude. And now we come to the part that, in 1998, genuinely shocked the cosmological community. Two independent teams of astronomers, Saul Perlmutter's team at Lawrence Berkeley National Laboratory and the team led by Brian Schmidt and Adam Rees at Harvard-Smithsonian, were both using a type of stellar explosion called Type 1a supernova as standard candles. Type 1a supernovae are useful as distance markers because they always explode with roughly the same intrinsic peak brightness. If you can measure how bright they appear, you can calculate how far away they are. If you know both their distance and their redshift, you can calculate how fast the universe was expanding at the moment their light was emitted, which is a window into the expansion history of the universe. Both teams were expecting to find confirmation of deceleration, the expansion slowing down as gravity did its work across cosmic scales. What both teams found instead was that distant supernovae were fainter than expected. Not brighter, fainter. They were further away than the decelerating expansion model predicted they should be. The expansion of the universe is not slowing down. It is speeding up. The universe is not decelerating under gravity. It is accelerating. The rate at which the gap between distant galaxies is growing is increasing over time. Not just expanding faster every year, every century, every billion years. This result was so unexpected, so fundamentally at odds with what cosmologists had assumed, that there was initially significant resistance. Both teams checked and rechecked their data. Independent groups checked both teams' work. The result was confirmed by completely independent lines of evidence, from the CMB, from the large-scale structure of galaxies, from gravitational lensing surveys. The result held. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery, and the thing causing the acceleration, the unknown component of the universe's energy budget that is driving the accelerating expansion, was named dark energy. What dark energy actually is remains one of the deepest unresolved questions in physics. The most popular candidate is a cosmological constant, an energy intrinsic to the vacuum of space itself, a baseline energy that empty space possesses simply by virtue of being empty. This is sometimes called vacuum energy, and it has a theoretical basis in quantum field theory, where the vacuum is not truly empty, but seething with virtual particles constantly popping in and out of existence, and where this quantum activity contributes an energy density to the vacuum. The problem is that naive calculations of the vacuum energy from quantum field theory give an answer that is roughly 10 to the power of 120 times larger than what is actually observed, a discrepancy so enormous that it has been called the worst prediction in physics. Something is cancelling out almost all of the quantum vacuum energy, leaving only a tiny residual that constitutes the observed dark energy. We do not know what. Chapter 5. The Future. Dark energy is writing. Let us run the models forward. Let us see where this goes. The first thing to understand is the distinction between gravitationally bound systems and unbound systems. Gravity operates locally. The expansion of space driven by dark energy operates everywhere, but locally, in regions where the density of matter is high enough that gravitational attraction outweighs the push of dark energy. Gravity wins. The Earth stays in orbit around the Sun. The Sun stays in the Milky Way. The Milky Way stays in the local group. Dark energy cannot pull apart systems that are gravitationally bound, because the gravitational force within those systems is stronger than the stretching of space on those small scales. The expansion of the universe does not make the Earth spiral outward from the Sun. It does not make the Sun drift out of the galaxy. The expansion operates on scales of megaparsecs and above, on the intergalactic scales where gravity is diluted by distance and dark energy finally wins. So the local group, the Milky Way, Andromeda, and the 50 or so dwarf galaxies orbiting both of them, will survive the expansion. In fact, the Milky Way and Andromeda are currently approaching each other, drawn together by their mutual gravity. In roughly 4.5 billion years, they will begin their first close encounter. In roughly 5 to 7 billion years, they will complete their merger into a single giant elliptical galaxy, sometimes called Milkomeda or Milkdromeda by cosmologists who need a name for it. All the dwarf galaxies of the local group will eventually be absorbed into this merged entity as well. The merged remnant of the local group will be our home for the indefinite future, a single large galaxy, containing the combined stars of everything that is currently our cosmic neighbourhood, floating in an increasingly empty universe. Because everything beyond the local group is another matter entirely. Right now, the Virgo cluster, the nearest major galaxy cluster, about 65 million light-years away, containing perhaps 1,300 galaxies, is receding from us at roughly 1,000 kilometers per second. The Coma cluster, one of the richest clusters in the observable universe, is about 320 million light-years away and receding faster still. All the other galaxy clusters, all the other superclusters, all the other structure in the universe that is not gravitationally bound to the local group is already moving away from us, already being carried off by the expansion, and the acceleration of that expansion means it is moving away faster every year. Over the next few billion years, the recession of these clusters will accelerate. Their light will begin to redshift more severely, shifting from visible wavelengths to infrared, then to radio waves, then to longer and longer wavelengths as they accelerate toward and eventually past our event horizon. The most distant clusters, already near the edge of our observable universe, will cross the event horizon first, then the intermediate ones, then, over trillions of years, even the nearer ones. In roughly 100 billion years, 7 times the current age of the universe, essentially all galaxies beyond the local group will have been carried past the event horizon. Our observable universe will have shrunk from containing roughly 2 trillion galaxies to containing one, the merged remnant of the local group, Milkdromeda, floating alone in the void, surrounded by nothing visible at all. Any civilization existing at that time, if any can survive that long, which is a remarkable and separate question, will look out at the sky and see no other galaxies. Not because the other galaxies do not exist. They will exist, still forming stars, still orbiting their supermassive black holes, still doing everything galaxies do, but they will be beyond the event horizon, receding faster than light, permanently inaccessible and permanently invisible. More than that, any civilization in that distant epoch will have no way of knowing that a universe full of 2 trillion galaxies ever existed. The CMB, the great cosmic fossil record of the Big Bang, will have redshifted to such enormous wavelengths that it will be undetectable. The expansion history of the universe will have become unreadable. The fundamental cosmological fact of our era, that the universe had a beginning, that it was once hot and dense and small, that it expanded from a singularity and grew into the structure we see today, will be unreachable from the evidence available to those future observers. In the very far future, past even the 100 billion year timescale, the stars in Milkdromeda will eventually begin to die. Massive stars burn out in millions of years. Sun-like stars burn out in billions. The faintest, most miserly red dwarfs, and there are many, many more of them than any other type of star, can burn for trillions to quadrillions of years, so slowly and so coolly that they squeeze every last erg of energy from their hydrogen fuel over timescales that make the current age of the universe look like a heartbeat, but even they will die eventually. One by one, the stars will burn out, leaving behind white dwarfs and neutron stars and black holes, dead remnants, dark and cold, the spent embers of the universe's stellar era. The galaxy will gradually dim over trillions of years, first losing its blue and white stars, then its yellow stars, then slowly even its red dwarfs, until what remains is a vast dark archipelago of stellar corpses orbiting a central supermassive black hole. And this is the state of the far future of the universe, a tiny remnant of our merged galaxy, dark and cooling, surrounded by an essentially infinite void. The gap between us and the next island of matter will be not millions or billions but trillions of light years. a gap so vast that light from those other remnants, already emitted before they crossed the event horizon, will be so redshifted as to carry essentially no energy by the time it reaches us. If it reaches us at all, the gap wins. Not dramatically, not with a bang or a catastrophe, but steadily, patiently, implacably. The expansion of space is the most patient force in the universe, and over sufficient time always comes. We are, in a very real sense, at the peak of cosmic density, the peak of cosmic connection, the moment when the most galaxies are visible, the most matter is accessible, the most of the universe's story can be read. It will never be more full than this. From here, in one direction, lies the hot young universe before stars formed. From here, in the other direction, lies the cold, dark universe after the stars go out. We are in the middle. We are in the light. We are living at the special time, perhaps the only time, or one of very few times, in the entire history of any civilization that could possibly exist in this universe, when the large-scale structure of the universe is visible, when the cosmic web can be mapped, when the CMB can be detected, when the Hubble constant can be measured, and the expansion history can be reconstructed, and the origin of the universe can be inferred from the evidence around us. In 1 trillion years, none of that will be possible. The evidence will have been swept away by the expansion. Future cosmologists, if they exist, will look at the sky and see essentially nothing, and they will have no way of knowing what they are missing. They will not be able to discover what we have discovered. The evidence will be gone. We are cosmologically lucky. Extraordinarily, improbably lucky. We exist in the brief window between the universe's birth, when it was too hot and dense for complex structure to form, and the universe's old age, when the expansion will have swept everything beyond reach. We exist at the moment when the most is visible, when the most can be known, and even now in this privileged moment, the gap is incomprehensibly large. Even now, the vast majority of the universe, by volume, by the raw spatial measure of what exists, is void, empty. The nothing between the galaxies, stretching across hundreds of millions of light years, containing almost no matter, no stars, no planets, no hope of any complexity arising, just the faint ghost of hot gas and the invisible threading of dark matter and the quiet, relentless push of dark energy driving the space apart. We have not yet talked about what it would actually be like to be in the void. We have not yet talked about the deeper physics of cosmic voids, about what the intergalactic medium actually does as the universe ages, about why the voids present some of the deepest puzzles in modern cosmology, or about what light endures on its way across the gap, a journey that is, in its own way, one of the most violent and transformative experiences in the universe. All of that is in part 2. But before we get there, I want you to hold something for a moment. You're on a planet orbiting a star inside a galaxy, inside a cluster, inside a supercluster, inside a cosmic web. You're surrounded. You're embedded in matter. You're connected by gravity and by light to hundreds of billions of galaxies. And all of it, everything you can see, everything you can measure, everything you can know about, fits into the bright 5 to 20% of the universe's volume that is not void. Everything we know, everything that has ever happened, every star that has ever burned and every planet that has ever formed, and every organism that has ever lived, is a thin cobweb of light, stretched across an ocean of darkness so vast and so empty that even describing it accurately feels like an act of violence against human intuition. The gap between galaxies is not a background detail, it is the main character. And in part 2, we are going to sit with it properly. Chapter 6, Stranded in the Void. Let us do something that no human being has ever done, and no human being will ever do. Let us go there. Let us place you right now in the interior of the Boots Void, not at the edge, not in one of the sparse filaments that weakly border it, right in the middle, at the geometric heart of a sphere of emptiness 330 million light-years across. Let us think carefully about what you would actually experience there, not just in terms of the numbers, but in terms of the reality of it, the sight, the physics, the complete and total severance from everything that has ever constituted a human environment. The first thing you would notice, assuming you are somehow equipped to survive the vacuum and the temperature, is the sky. On Earth, on a clear night far from city lights, You can see roughly 5,000 stars with the naked eye. You can also see a few other galaxies if you know where to look. The Andromeda Galaxy is technically visible as a faint smudge, the Magellanic Clouds are visible from the southern hemisphere, and a handful of other objects are detectable under exceptional conditions. The night sky, even at its darkest and clearest, is populated. It is a sky that has never been empty, not once. In the history of human civilization, not even for a single person who ever lived on this planet. In the heart of the Bhuta's void, the sky would be different in a way that would be, without exaggeration, psychologically shattering. There would be no stars, not fewer stars, no stars. The nearest star, the nearest individual star to you in any direction, would be tens of millions of light years away, inside one of the galaxies on the void's boundary. The nearest galaxy would be roughly 165 million light years away, a point of light so faint, so distant, so redshifted that it would be invisible to the naked eye. You would need a telescope just to find the nearest galaxy. And having found it, you would see not a galaxy but a point. A dim, almost colourless point lost in a sky that was, by any human measure, absolutely and terrifyingly black. The Milky Way, your home, the galaxy you came from, would be about 165 million light years away from you in one direction. Andromeda, roughly the same distance in another. The entire local group would be a smudge too faint to see without instruments, in a sky populated by nothing. Nothing above you, nothing below you, nothing to your left or right. A sky of pure black, in every direction, as far as the best telescope you could build could possibly see. And here is the psychological dimension of this that I want to sit with for a moment because I think it is important. Human beings are fundamentally creatures of context. We derive our sense of location, our sense of scale, our sense of being somewhere rather than nowhere, from the objects around us. The stars in our night sky, faint as they are our context. They tell us we are in a galaxy, in a populated cosmic neighbourhood, on a planet that is one of many. They connect us to the larger structure of the universe. They are the evidence that the universe exists at all. In the heart of the Bhuta's void, that context would be gone. You would have no stellar evidence that the universe exists at all. You would have, if your instruments were sensitive enough, the cosmic microwave background, a faint 2.7 Kelvin hiss of microwave radiation coming equally from all directions, the afterglow of the Big Bang. That would be your only reliable evidence that you are in a universe at all, rather than floating in some absolute perfect eternal nothing. The CMB would be cold comfort, to put it mildly. Now let us add the physics. The temperature of intergalactic space in the void is determined by two things. The CMB, which maintains space at about 2.7 Kelvin, about minus 270 degrees Celsius, a fraction of a degree above absolute zero, and the WIM, the warm-hot intergalactic medium, which is technically at millions of Kelvin but so vanishingly sparse that it would deposit effectively no heat in any human-scale object. You would freeze, not quickly and dramatically in the way science fiction sometimes depicts, but relentlessly and absolutely, radiating your heat into a background that is colder than anything that naturally exists on Earth. The density of the void interior is, as we discussed in part 1, somewhere around 1 to 10 atoms per cubic meter. In practical terms, this means that a human-sized object in the void would encounter roughly a handful of particles per second. Not enough to cause any physical effect whatsoever. Not enough to hear, not enough to feel, not enough to detect without extraordinarily sensitive instruments. You would be surrounded by something so close to nothing that the difference between the void and true vacuum would be philosophically interesting and physically irrelevant. And the silence would be absolute. Sound requires a medium, pressure waves propagating through matter. In the void, the matter density is so low that even the concept of sound becomes meaningless. There is no medium in which a wave could propagate. There is no pressure difference between adjacent regions. The void is not just quiet. It is a place where quiet is the wrong word, because quiet implies the absence of sounds that could in principle be present. In the void, sound is not absent. Sound cannot exist. The very physics required to support the phenomenon does not apply. Now, let us add the time dimension. You are in the heart of the Bhuta's void. You have somehow survived. You have your instruments. You're looking at the distant boundary of the void, where a few sparse galaxy filaments mark the edge. of the emptiness. You decide to try to reach the nearest galaxy. You're a point in space, and the nearest concentrated matter is roughly 165 million light-years away. Even at the speed of light, which no physical object can actually achieve, the journey to the nearest galaxy would take 165 million years. The Earth formed 4.5 billion years ago. Complex animal life has existed on Earth for perhaps 600 million years. Hominids have existed for perhaps 6 million years. Homo sapiens for roughly 300,000 years. Civilization for perhaps 10,000 years. The time it would take, travelling at the maximum possible speed permitted by physics, to reach the nearest galaxy from the centre of the Buta's void is 165 million years, more than 500 times longer than the entire history of complex animal life on Earth. At any velocity a human spacecraft has ever achieved, say the roughly 17 kilometers per second of Voyager 1, the journey would take not 165 million years but something closer to 3 quadrillion years, 3 times 10 to the power of 15 years. The current age of the universe is 13.8 billion years, or roughly 1.38 times 10 to the power of 10 years, so the journey would take about 200,000 times longer than the current age of the universe. You would die in the void. Not because of any dramatic physical event, not because of radiation or pressure or impact, but because the void is simply too big, and time is finite, and the distance between you and the nearest matter is a number that cannot be survived by any biology or any technology we can currently conceive of. The void does not kill you. The void simply makes reaching anything else impossible. Chapter 7. Light's Impossible Journey. Now let us think about what happens to something that can actually make the crossing. Something that moves at the speed of light. Let us think about light itself. A photon leaving a distant galaxy and making the long, improbable journey across the intergalactic medium to reach your eyes or your telescope. Because the journey of light across intergalactic space is not a passive, uneventful cruise, it is a long and transformative ordeal, and the things that happen to light on that journey are among the most important tools we have for understanding the universe we live in. The first thing that happens to light as it crosses the expanding universe is redshift. As space expands, the wavelength of light travelling through it stretches, like a wave drawn out on a rubber band as you pull the band longer. A photon emitted by a galaxy 1 billion light-years away, over the course of its billion-year journey, will have its wavelength stretched by the expansion of space by a factor of roughly 1.07. It arrives about 7% redder than when it left. A photon from a galaxy 10 billion light-years away arrives with its wavelength roughly doubled. A photon from the very edge of the observable universe, from the epoch of the CMB, about 13.8 billion years ago, arrives having had its wavelength stretched by a factor of about 1,100. What began as visible or ultraviolet light has been stretched all the way to microwave wavelengths. This is why the CMB is microwave radiation. The photons of the CMB were emitted when the universe was about 380,000 years old and was hot enough to glow brightly in visible light. Those photons have been travelling for 13.8 billion years, and the universe has expanded by a factor of 1,100 since then, stretching their wavelengths by that same factor, cooling them from visible light to microwaves. When you detect the CMB, you're detecting light that left its source when the universe was less than 0.003% of its current age, transformed by 13.8 billion years of cosmic expansion into something that would be invisible to the naked eye. But redshift is not the only thing that happens to light on its intergalactic journey. There is absorption, there is scattering, and in some epochs of the universe's history, there was an environment so hostile to light that photons could not travel freely at all. To understand this, we need to go back to a time before the cosmic web existed, before galaxies, before stars, to what cosmologists call the Dark Ages. After the CMB was emitted, after the universe had cooled enough for electrons to combine with protons and form neutral hydrogen, in an event called recombination, the universe entered a period of profound darkness. There were no stars, there were no galaxies, there was no luminous matter of any kind. The universe was filled with a nearly uniform fog of neutral hydrogen and helium gas, and that fog was dark. Not just dim, not just faint, but utterly without light. The only photons present were the CMB photons, and they were rapidly cooling and redshifting and becoming less energetic. The universe, for perhaps 150 to 200 million years after the Big Bang, was completely, absolutely dark. This was the universe's dark ages, and it lasted until the first stars formed. The first stars, population 3 stars, the term cosmologists use for stars, formed entirely from the primordial hydrogen and helium of the Big Bang, with no heavier elements at all, were almost certainly very different from the stars we see today. With no heavy elements to act as cooling agents in collapsing gas clouds, the gas had to collapse further and heat more before the pressure was sufficient to ignite fusion, which meant the first stars were likely extremely massive, perhaps hundreds of times the mass of the Sun, and extraordinarily luminous, burning hot and fast and dying young in tremendous supernova explosions that seeded the surrounding gas with the first heavy elements. And when those first stars ignited, something remarkable happened to the intergalactic medium. The ultraviolet radiation pouring from those massive hot stars began to ionize the surrounding neutral hydrogen, stripping electrons from hydrogen atoms, converting the neutral gas into a plasma of free protons and electrons. This process, which spread outward from the first stars and galaxies in expanding bubbles of ionized gas that eventually grew and merged and overlapped until the entire intergalactic medium was ionized, is called the Epoch of Reionization. The Epoch of Reionization was not a brief event. It was a process that unfolded over hundreds of millions of years, roughly between 150 million years and 1 billion years after the Big Bang, and it transformed the intergalactic medium from a fog of neutral gas that was largely opaque to ultraviolet light into the transparent, highly ionized medium that exists today. The light from the very first galaxies had to fight its way through a universe that was still in places filled with neutral hydrogen, every photon absorbed and re-emitted by countless hydrogen atoms, scattered and delayed and transformed on its way out. If you look at the spectra of very distant quasars, objects at redshifts of 6 or above, meaning their light was emitted when the universe was less than 1 billion years old, you see something called the Gunn-Peterson trough, a nearly complete absorption of the quasar's light at wavelengths blueward of the Lyman alpha line. This is the signature of neutral hydrogen in the intergalactic medium absorbing essentially all of the quasar's short wavelength light before it can reach us. At lower redshifts, looking at more recent closer objects, this absorption is much weaker because the intergalactic medium is almost completely ionized and therefore mostly transparent. The transition between these two regimes, the period when the Gunn-Peterson trough goes from deep and complete to shallow and patchy, is our window into the epoch of reionization. We can, by carefully studying the spectra of distant quasars, trace the history of how the universe went from opaque to transparent, from dark to lit, from the void of the Dark Ages to the illuminated cosmic web we see today. And what all of this means for light's journey across the intergalactic medium is that the medium itself has a history. The same journey that a photon makes today, crossing hundreds of millions of light years of nearly empty space, barely disturbed, arriving with only the imprint of its redshift to show for the crossing, would have been a completely different experience for a photon making the same crossing during the epoch of reionization. It would have encountered patches of neutral hydrogen, been scattered and absorbed and re-emitted, been transformed and delayed. The transparency of the intergalactic medium that we take for granted today is not a permanent feature of the universe. It is a phase that was preceded by opacity, and that will, in the far future, be followed by something stranger still. There is also the matter of what the intergalactic medium does to light in subtler ways, even in its current nearly transparent state. The diffuse gas of the WIM, the weak intergalactic magnetic fields, the cosmic ray electrons spiraling along those fields, all of these leave faint but detectable marks on light passing through them. The Faraday rotation of the polarization plane of radio waves by magnetic fields, the scattering of X-rays by hot electrons, the thermal Sunyaev-Zeldovich effect, in which CMB photons passing through hot electron plasmas in galaxy clusters are boosted to slightly higher energies, leaving a characteristic imprint on the CMB that allows us to detect the presence of galaxy clusters we might not be able to see directly. Light, on its journey across the gap, is not just a passive messenger, it is an instrument. Every interaction it has with the intergalactic medium leaves a mark that we can read, if we are clever enough, as a record of what the medium was and where it was and what it was doing. The Gap writes its autobiography in The Light That Passes Through It. Chapter 8, The Dark Energy Problem. We have been talking about dark energy throughout this video, invoking it as the cause of the accelerating expansion, noting that it makes up roughly 68% of the universe's total energy budget, pointing out that its nature is unknown. But I want to spend some time now actually sitting with how unknown it is, because I think the depth of our ignorance about dark energy is one of the most important and underappreciated facts in all of science. Let us be precise about what we know and what we do not know. What we know, the expansion of the universe is accelerating. This is one of the most robustly confirmed facts in modern cosmology, supported by multiple independent lines of evidence. Type 1, a supernovae, the CMB baryon acoustic oscillations, the fossilized imprint of sound waves in the early universe, visible in the large-scale distribution of galaxies, which act as a cosmic ruler, allowing us to measure how fast the universe has expanded at different epochs. Weak gravitational lensing surveys. All of these methods, using completely different physics and completely different observations, give consistent results. The expansion is accelerating. What we know, the acceleration requires something. Some component of the universe's energy budget that has negative pressure, a property that, in the context of general relativity, acts to accelerate rather than decelerate the expansion. This is deeply counterintuitive. Normal matter and radiation have positive pressure, which in the context of cosmology contributes to decelerating the expansion. Something with negative pressure, something for which the act of expanding actually releases energy rather than consuming it, is required to produce the observed acceleration. What we know, whatever this thing is, it makes up roughly 68% of the total energy density of the universe. It is the dominant component of the universe's energy budget. The universe is 68% dark energy, 27% dark matter, and about 5% everything else. All the ordinary matter, all the stars, all the galaxies, all the planets, all the gas, every photon, every neutrino, every proton and neutron and electron that has ever existed. 95% of the universe by energy is stuff we do not understand. 5% is stuff we do understand. And that 5% is everything we have ever been able to directly observe, touch, measure, or interact with in any way throughout the entire history of our civilization and our species. What we do not know, almost everything about what dark energy actually is. The simplest model is the cosmological constant, lambda, the symbol Einstein introduced into his field equations, and then famously called his greatest blunder before later evidence vindicated it. A cosmological constant is a fixed energy density that belongs to the vacuum of space itself. It does not dilute as the universe expands. It does not clump or cluster. It is the same everywhere and every when. As the universe expands and ordinary matter becomes more dilute, the cosmological constant remains fixed, and so its relative contribution to the energy budget grows over time. In the early universe, when matter was dense, the cosmological constant was negligible. In the current universe, as matter has been diluted by expansion, the cosmological constant now dominates. The problem with the cosmological constant as an explanation for dark energy is not observational. It fits the data extremely well. The problem is theoretical. Quantum field theory predicts that the vacuum should have an energy density arising from the zero-point fluctuations of all the quantum fields that permeate space. The problem is that when you try to calculate this vacuum energy density from first principles using quantum field theory, you get an answer that is roughly 10 to the power of 120 times larger than the observed value of the cosmological constant, 10 to the power of 120. This is often cited as the largest discrepancy between theory and observation in all of physics. You might think that a factor of 10 to the power of 120 sounds like a calculation that is simply wrong, that the quantum field theory calculation must be making some naive error that, once corrected, would give the right answer, and you might be right. But the problem is that despite decades of effort from some of the most brilliant theoretical physicists in the world, no one has found a satisfying explanation for why the vacuum energy should be so small. The answer we observe, a cosmological constant just large enough to be causing the accelerating expansion we see, is, from the perspective of quantum field theory, absurdly, inexplicably small. It is as if you calculated the weight of a person and got a trillion tons, but when you put them on a scale it reads 70 kilograms. Something is cancelling the quantum vacuum energy almost completely, leaving only a tiny residual. Whatever that something is, we do not know what it is. This is called the cosmological constant problem, and it is, by some measures, the most profound unsolved problem in fundamental physics. The alternative to a true cosmological constant, a fixed, unchanging vacuum energy, is a dynamic dark energy, often called quintessence. Quintessence is a hypothetical scalar field that pervades all of space and whose energy density changes slowly over time. Unlike a true cosmological constant, quintessence can in principle vary from place to place and from epoch to epoch, though its variations would be very slow and very smooth. The key observational difference between a cosmological constant and quintessence is the equation of state. For a true cosmological constant, the ratio of pressure to energy density, called W, is exactly -1. For quintessence, W can take other values, or it can evolve over time. Current observations constrain W to be very close to -1, consistent with a cosmological constant. But the uncertainty is not zero, and in 2024, a major collaboration called DESI, the Dark Energy Spectroscopic Instrument, which measured the three-dimensional positions of tens of millions of galaxies using baryon acoustic oscillations, announced results suggesting that the equation of state of dark energy might not be constant, the W might be evolving over time. If this result holds up as more data comes in, and as of my knowledge cutoff, the statistical significance was tantalizing but not yet at the level required for a definitive claim. It would be one of the most important cosmological discoveries in decades. It would rule out a true cosmological constant and point toward a dynamic dark energy, something that is not a fixed property of empty space but a field, evolving and changing, whose future behaviour we could not confidently predict from its current state. There are also proposals that go further than quintessence. Modifications to general relativity on cosmological scales, theories in which gravity behaves differently over enormous distances than it does in our local solar system. Theories in which the universe has extra dimensions whose effects become important at large scales. Theories in which what we call dark energy is actually an artifact of living in an unusual region of the universe. None of these has yet produced a compelling fit to all the data, and the cosmological constant remains the simplest and most observationally consistent description. But here is what I want you to take away from all of this. The dominant force in the universe, the thing that controls the large-scale behaviour of everything, the thing that is currently winning the cosmic battle against gravity, the thing that is steadily widening the gap between galaxies and will eventually push everything beyond the reach of everything else, is something we have been unable to explain for more than 25 years since its discovery, despite it making up 68% of all the energy in the universe, despite the best efforts of hundreds of thousands of physicists and cosmologists, despite the most sophisticated theoretical and observational tools humanity has ever built. We do not know what dark energy is. We do not know why it has the value it has. We do not know whether it will remain constant or change over time. We do not know, therefore, whether the future I described in Part 1, the steady, patient widening of the gap until every galaxy is lost beyond the horizon, is the actual future of the universe, or whether something will change, whether dark energy will fade away and let gravity eventually win, or whether dark energy will strengthen and tear apart not just the cosmic web but galaxies themselves, and then solar systems, and then planets, and then atoms, in an event cosmologists call the Big Rip. The gap between galaxies is real. It is growing. And the thing that is growing, it is the deepest mystery in science. Chapter 9. The Big Rip and Other Futures. The future I described in Chapter 5, the steady isolation of the local group, the fading of the stars, the long cooling dark, was a future calculated under the assumption that dark energy is a cosmological constant, that its density remains fixed forever. But let us spend some time thinking about the other possibilities, because the gap is not just a present-day feature of the universe. It is a narrative about where everything is going, and the ending of that narrative depends critically on what dark energy actually is. The most dramatic possible future, given dark energy, is the Big Rip. The Big Rip is a scenario that occurs if the equation of state of dark energy, the ratio of its pressure to its energy density, is less than -1. In other words, if the energy density of dark energy increases as the universe expands, rather than remaining constant or decreasing. In this scenario, dark energy does not just accelerate the expansion at a fixed rate, it accelerates it at an accelerating rate. The expansion becomes faster and faster, not just over billions of years, but over millions, then thousands, then years, then seconds, until the rate of expansion becomes infinite in a finite amount of time. What this means physically is that the expansion eventually becomes strong enough to overwhelm not just the gravity-holding galaxy clusters together. It would do that first, ripping apart the cosmic web, but the gravity-holding individual galaxies together, and then the gravity-holding solar systems together, and then the gravity-holding planets together, and then the electromagnetic forces holding molecules together, and then the nuclear forces holding atomic nuclei together, until, at the final moment before the singularity of infinite expansion, every particle in the universe is causally disconnected from every other particle, each one alone in its own infinitesimal, infinitely expanding universe. Current observations give a value of W consistent with -1, meaning the Big Rip is not favoured by current data, but the constraints are not tight enough to rule it out completely. If W is even slightly less than -1, if dark energy is even slightly of the phantom energy variety, with an energy density that grows with expansion, then the Big Rip is in our future. The uncertainty in the measurement of W leaves this door open. There is also the possibility of the Big Crunch. This is the old scenario, the scenario cosmologists believed in before 1998, in which the universe eventually stops expanding and begins to contract, all matter falling back toward itself under gravity, the expansion reversing into collapse, the universe ending in a hot, dense singularity that mirrors the Big Bang. This scenario requires either that dark energy eventually fades away and gravity wins, or that the total density of the universe is above the critical density, the density at which gravity is strong enough to halt and reverse the expansion. Current measurements of the universe's density suggest it is very close to the critical density. Cosmologists say the universe is spatially flat, meaning its geometry follows Euclidean rules at the larger scales, which corresponds to being at or very near the critical density. But dark energy makes up 68% of the energy budget, and dark energy has negative pressure, which means it acts against gravitational collapse. Under the standard cosmological constant model, the Big Crunch is not in our future. The expansion will continue forever. But if dark energy is dynamic, if it fades over time, as some quintessence models predict, then the balance could shift. At some future epoch, if dark energy weakened enough, the matter and dark matter in the universe could begin to reassert gravitational dominance, slowing the expansion and eventually reversing it. The gap between galaxies would stop growing, begin to shrink, and the universe would begin the long, catastrophic fall back to a singularity. There is even, in some scenarios, a cyclic universe, a Big Crunch followed immediately by a Big Bang, an eternal oscillation of expansion and contraction, with each cycle perhaps producing a universe with slightly different physical constants, or perhaps identical to the last, the same drama playing out again and again in an infinite loop. This is speculative in the extreme. We have no observational evidence for a previous cycle, and the theoretical machinery for a truly cyclic universe is not yet in a form that makes clean, testable predictions. But it is a live possibility in the minds of serious cosmologists, and then there is what might be called the cold, quiet end. In the standard cosmological constant model, the most observationally favoured scenario, the universe neither rips apart nor collapses. It simply expands forever, cooling forever, with the gap between galaxies growing forever. This is sometimes called the heat death or the big freeze. Not a dramatic end, but a slow, patient approach toward maximum entropy and minimum temperature. The stars go out. The black holes slowly evaporate through Hawking radiation over incomprehensibly long timescales. A supermassive black hole might take 10 to the power of 100 years to fully evaporate. The protons, if they are unstable as some theories predict, decay on timescales of 10 to the power of 34 years or more. Eventually, even the electrons and positrons drift apart, separated by the expanding void, until the universe is a thin, cold, nearly empty gas of fundamental particles at near zero temperature, expanding forever into a void that grows forever. The gap wins every scenario except the Big Crunch, and even in the Big Crunch, the gap wins first, growing enormous and terrible before gravity finally reasserts itself and reverses the trend. The universe appears to be built around emptiness. The gap is not an accident or an afterthought. It is the dominant structure, the dominant feature, the dominant fate. Chapter 10. What the void means. I want to spend some time now on something that science sometimes neglects. The question of what it all means. Not in a cosmic spiritual sense, but in the more grounded sense of, given everything we have covered, how should we think about our situation? What does it mean to live in a universe that is, by volume and by destiny, almost entirely empty? There is a view of the universe that has been common in popular science communication for a long time, a view that emphasizes the richness, the abundance, the extraordinary complexity of the cosmos. The universe is full of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of those stars orbited by planets, many of those planets potentially habitable, potentially populated. The universe is teeming. The universe is overflowing with possibility. And there is truth in that view. There is genuine wonder in the sheer number of stars and the sheer number of possible worlds. The universe is, by the measure of things that matter to life, extraordinarily rich. But it is also, by the measure of volume, extraordinarily empty. And I think both of these things deserve to be held simultaneously, because they are both true, and the tension between them is one of the most interesting features of the universe we actually live in. Here is a useful way to think about it. Every galaxy in the observable universe, every one of those 2 trillion galaxies, is, from the perspective of the void, a speck. A tiny, isolated island of density in a vast ocean of nothing. The average spacing between galaxies, as we calculated, is a cube of space 3.4 million light-years on each side. That cube is, apart from the one galaxy at its center, almost perfectly empty. And in the voids, the regions between the filaments, even that sparse average is wildly optimistic. The void interior is emptier than the average by many orders of magnitude. We live on a pale blue dot orbiting an unremarkable star in the outer suburbs of a galaxy that is, from the perspective of the void, simply one speck among 2 trillion, and that galaxy is surrounded in almost every direction by hundreds of millions of light-years of almost nothing. The nearest other speck, the Andromeda Galaxy, is 2.5 million light-years away. And between us and Andromeda there is, by any honest accounting, a great deal of absolutely nothing. Does this diminish us? Does the emptiness of the void make the complexity of life and consciousness and civilization somehow smaller or less significant? I would argue the opposite. The fact that complexity, that stars and planets and chemistry and life and intelligence exists at all in a universe that is overwhelmingly empty is, on reflection, one of the most remarkable things about the universe. Not because the universe was designed to produce complexity, which is a claim beyond the scope of physics, but because the physical laws that govern the universe happen to be the kind of laws that, given a sufficiently long time and the right initial conditions, produce this extraordinary efflorescence of structure and organization in the tiny fraction of space that is not void. The void is the default. The filaments, the galaxies, the stars, the planets, the chemistry, the life. These are the exception. They are what happens when gravity concentrates matter against the general tendency of the universe toward dispersion and emptiness. They are the universe folding back on itself briefly in specific places to produce something complicated and interesting, before the expansion carries it all apart again. We are that something. We are a brief, local, improbable folding of matter against the void. We are complexity produced temporarily by a universe that is overwhelmingly and increasingly simple, and the fact that we can look at the void and understand the void and feel the appropriate vertigo at the scale of the void, that is not nothing. That is, in some sense, the universe's most remarkable trick, producing, in a tiny corner of itself, something capable of understanding how empty the rest of it is. There is something else about the void worth saying here, which connects to a theme we touched on in part 1, the question of our cosmic timing. We established that we are living at what may be the optimal moment for cosmology, the epoch when the large-scale structure of the universe is most legible, when the CMB is still detectable, when the 2 trillion galaxies of the observable universe are still within reach of our telescopes. Future civilizations, if they exist in the far future, will inherit a universe stripped of all this context, unable to do the cosmology we can do today. But there is a flip side to this. The fact that we are at the peak of cosmic legibility means we are also at the peak of cosmic isolation. The gap between our galaxy and its neighbours is already enormous. The expansion is already well underway. The universe has already spent 13.8 billion years emptying its voids and growing its gaps and carrying its galaxies apart. We are not at the beginning of this process. We are in the middle of it, perhaps past the middle of it. And yet, even now, even at this relatively late stage in the universe's expansion, we are close enough to other galaxies to detect them, close enough to study them, close enough to do the cosmology that lets us understand our situation. We are far enough from the Big Bang that life and intelligence could evolve, but close enough to the Big Bang that the universe still has enough structure to read. This is a remarkable coincidence of timing, or perhaps not a coincidence at all. Perhaps any civilization that could possibly exist had to arise in roughly this epoch, because earlier the universe was too simple, and later the universe will be too empty. Perhaps the window for intelligent cosmology doing life is not infinite but finite, bounded on one side by the time it takes for stars and planets and evolution to run their course, and on the other side by the time it takes for dark energy to empty the visible universe of everything interesting. If that is true, and it is a plausible argument, not a certainty, then we are not just living at a special time by chance. We are living at the only time when it is possible to be a species sophisticated enough to understand what the void is and to still have the cosmic context necessary to figure it out. Chapter 11. The signals we send into the void. There is one more aspect of the gap that I want to address before we close, and it is one that connects the abstract physics of the void to something more immediate and human. In 1974, astronomers used the Arecibo radio telescope to send a message toward the globular cluster M13, a dense group of stars about 25,000 light-years away. The Arecibo message was a brief burst of radio waves encoding in binary a simple description of human biology, chemistry, and the solar system. It was the first deliberate broadcast from Earth intended to be received by a hypothetical technological civilization elsewhere in the galaxy. The message has been travelling at the speed of light for about 50 years. It has covered about 50 light-years. M13 is 25,000 light-years away. The message will arrive in about 24,950 years. A reply, if one were sent immediately upon arrival, would reach Earth about 50,000 years from now. This is communication across interstellar space, within a galaxy. The round-trip time is 50,000 years. Now consider sending a message across intergalactic space. To the Andromeda Galaxy, 2.537 million light-years away. A signal sent today would arrive in 2.537 million years. A reply would return 2.537 million years after that, 5.074 million years after transmission. And that is the nearest large galaxy. That is the easiest intergalactic conversation you could possibly attempt. For the Virgo cluster, 65 million light-years away, the round-trip time for a signal is 130 million years. For a galaxy in the Coma cluster, 320 million light-years away, a round-trip conversation takes 640 million years. For a galaxy at the edge of the observable universe, you could not even begin a conversation. By the time your signal arrived, they might be beyond your event horizon, and their reply, even if sent immediately, might never reach you. The void does not just separate us physically, it separates us communicatively, it separates us causally. Galaxies are not just far from each other, they are, for any practical purpose, incapable of affecting each other in any directed, information-rich way. The universe is not a network of connected civilizations sharing information across the cosmic web. It is, for any civilization that might exist anywhere in it, a prison of isolation defined by the speed of light and the scale of the gap. If there are other civilizations in other galaxies, and there may well be, given the numbers involved, then not only have we never heard from them, but we could never hear from them on any timescale relevant to a civilization. Not because they lack technology, not because they lack the will to communicate, but because the gap is simply too large, and time moves too slowly, and the universe's expansion is steadily making the already impossible more impossible with every passing year. We are, on the intergalactic scale, completely alone. Not in the sense that nothing else exists. The universe likely teems with complexity somewhere in its 2 trillion galaxies, but in the sense that no information about that complexity can ever reach us on any civilizationally meaningful timescale. Whatever dramas are playing out in the Virgo cluster, whatever civilizations might have arisen and flourished and ended in the Andromeda galaxy, whatever light shows might be happening in the filaments and walls of the cosmic web, we will never know. The gap prevents it. The gap does not care. This is one of the truths about the universe that I think deserves to be held directly and honestly, without being softened by optimistic framing. The universe is not scaled for communication between galaxies. It is not scaled for interaction between galaxies. It is scaled for isolation between galaxies. The gap is not a temporary obstacle that a sufficiently advanced civilization could overcome. It is a feature of the universe's geometry, enforced by the finite speed of a light and amplified by the accelerating expansion of space that makes intergalactic connection not just difficult, but, for any directed communication, essentially impossible in any relevant sense. We are on our island. The other islands exist. They will always be too far away. Conclusion. Let me bring you back to where we started. You are sitting on a planet orbiting a star inside a galaxy. You are surrounded, and you are also, as we now understand in full, stranded on a tiny island of matter in the middle of an ocean of emptiness so vast that it would take the entire history of complex animal life on Earth, travelling at the speed of light, just to cross from one edge of the nearest void to the other. You're in a universe that is 80 to 95% nothing by volume. You're in a universe where the dominant force, dark energy, 68% of all the energy that exists, is something we cannot explain, whose nature is unknown, and whose ultimate behaviour could determine whether the universe ends in a slow freeze or a sudden rip or a distant crunch. You're in a universe where the gap between your galaxy and the rest of the cosmic structure is growing faster every year, and where, given enough time, everything you can see will be carried beyond the reach of any possible signal. And you are doing all of this, existing, thinking, feeling the vertigo of these scales, in the brief, improbable window between the universe's hot, chaotic beginning and its cold, empty end, at what may be the optimal moment in all of cosmic history for a creature to look up and understand what it is looking at. The gap between galaxies is not just an astronomical fact. It is the dominant context for everything that exists. It is the ocean we swim in, even if we can only see the tiny island we are standing on. It is the fate we are sailing toward, even if we are so small, and the ocean is so vast that the sailing takes longer than any human imagination can encompass. But here is what I keep coming back to. Here is the thing that, for me, transforms the vertigo of the void from pure existential terror into something more complicated and perhaps more interesting. The void is indifferent. The void does not know we are here. The expanding space between galaxies is not hostile. It is not anything. It is just empty geometry obeying equations that have no awareness of the matter threading through them. The gap does not care. The dark energy driving the expansion does not target us. The isolation enforced by the finite speed of light and the accelerating cosmos is not a punishment. And yet we, this particular collection of atoms on this particular planet around this particular star in this particular galaxy, we know about it. We measured it. We sent telescopes into orbit and pointed them at dim spots in the sky, and counted the galaxies and measured their redshifts and reconstructed the expansion history and calculated the equation of state of dark energy and mapped the cosmic web and simulated the formation of the voids and discovered that we are in one of them, that the universe we live in is mostly empty in ways that would take many lifetimes to fully describe. We did all of that. A species that has been doing science for a few hundred years, that has been technologically capable of doing cosmology for perhaps a century, that evolved from simpler organisms on a wet rock orbiting an ordinary star in the unfashionable outskirts of an unremarkable galaxy. The universe is vast and mostly empty, and growing more empty all the time, and we know that. We figured it out. The gap between galaxies is even worse than you thought when this video started. It is larger than the numbers suggested, emptier than the words implied, more permanent than you wanted to believe, and more dominant than the maps made it seem. It is the universe's primary characteristic, The void is what the universe is. The rest, the filaments, the galaxies, the stars, the planets, us, is the exception. But the exception is the only part that knows it is an exception. And I think that means something, even if the universe does not agree.